One final example of being able to work with integration by parts. This one seems like a fairly simplistic integral, cos ln dx. If we were to ask to find the derivative of it, it would be really easy, just a chain rule. This one's going to be one of those iterated integrals, but we're going to define u to be equal to the cosine of ln of x. And then when we take the derivative of that, that's going to be our chain rule. All right, so du is going to be equal to the opposite of sine ln x. And the derivative of natural log x is going to be 1 over x. And there's a dx right there because we took the derivative with respect to x. So what does that make dv? Well, dv is going to be equal to dx. Okay, so you might remember that example to where if we're not necessarily sure, then dv is going to be dx, and v is going to be equal to our x. Now, one last thing. I'm going to call this integral I. Because what we're going to notice is that it's going to be that type to where it's going to be an iterated integral, and we're just going to keep spinning our wheels if we keep trying to use parts too many times. By parts, u, v, v, du. And so the original integral I is going to be equal to x cos ln x minus the integral of v du, which is going to be x sine ln x divided by x dx plus c1. All right, now this actually works out fairly nicely with simplification, but then we have to do a little bit more integration with this. All right, and there should be a negative in here. All right, so the x's are going to cancel out. This is going to turn into a positive, so no big deal. So this is going to turn into I is going to be equal to x cos ln x plus the integral of sine ln x dx plus c1. All right, so this integral sine ln x dx actually looks really close to the original, except instead of a cos, we have a sine. So we're going to use the exact same technique to be able to evaluate a remaining integral. I'm going to let u be equal to sine of ln of x. The derivative of sine is cosine. We have a chain rule. The derivative of natural log is 1 over x. And since the derivative with respect to x, we're going to have a dx in there. We also have to go through and take the antiderivative of this dx. So dv is dx, v equals x. So uv, v du once again. We still have all of this that we started with. So that's just going to drop down. We have our constant of integration, c1. So our integral I is going to be equal to x cos ln x. We have uv, which is going to be plus x sine x. Okay, so again, I have our uv x sine ln x minus the integral of v du. All right, and so that's going to be x cos ln x over x dx. I'm just going to call this plus c2. All right, and so just like before, x's are going to cancel out. And what are we left with? So it looks like that we're going to be left with, once again, another integration by parts. So I is going to be x cos natural log x plus x sine ln of x minus the integral of cos ln x dx plus c2. All right, now at this point, we have to be careful because if we do by parts again, we're not going to get too far with it because we're just going to end up with the exact same thing that we started with, except it's negative. All right, so, but if we're smooth about this, And we recognize at the very beginning that we called the integral of cos ln x dxi. That's exactly what we have here. So this animal right here is our I. And so we're going to write this as I equals x cos ln x plus x sine ln x minus I plus C2. And in fact, we could just call it C if we wanted to, but we're almost done with it. We're going to add I to the other side. It's going to be an algebraic equation. So we get 2I equals x cos ln x plus x sine ln x plus C2. And finally, we can divide both sides by 2. One possible answer is that the integral I is going to be equal to x cos ln x divided by 2 plus x sine ln x divided by 2. And I'm just going to call it plus constant c. All right. Or we could factor out the x over 2 to make it nice. Although if you got to this point, this is a perfectly acceptable answer in my book. But if you wanted to factor out an x over 2, we could write this as cos of ln x plus sine of ln x plus constant of integration c. All right, so we've taken a look, and just to summarize all different types of integration by parts problems we've looked at, and there's 3 of them. Okay, so summary. All right, so we had the basic type where we just use the formula integral of u dv is equal to uv minus integral v du. And we might have had to do it a few times, but we were able to get to the answer. The second type was where we had to define dv to be dx. And usually that occurred in an integral, if you remember, ln x dx. And then we had the other integral where we had the integral of arc cos x dx. And I think it was a finite or a bounded integral, right? And then the last type was where we had to have I equals the integral, the iterated integral. So for instance, we had the integral of cosine of ln x dx, and we had to solve it in terms of I by doing a couple integration by parts. All right, so those are the 3 different types of integration by parts, at least for now, that we're going to look at. There's a lot more difficult types, but this, again, since we're just an introduction to integral calculus, these are probably going to be the most rigorous that you're going to be faced with on an examination.